Welcome to this second video in Unit 3 on probability theory. Today we are going to be talking about probability distributions, and as always this is presented by Eduonics. In this lecture we're going to introduce random variables, and in combination with those random variables we'll talk about probability distributions for both discrete and continuous variables, some special distributions, and other things that you might see. This will focus on more of the theory, some of the notation. Probability distributions are used ubiquitously throughout AI and machine learning research in general. As a result, it's essential that we cover them so that we can have an understanding of normalization and these different distributions that are getting used throughout this type of work. So let's go ahead and dive right in and see if we can learn something new. Alright, so to start we have random variables, and a random variable is simply a variable that can take on different values randomly. That may seem repetitive, but it is just an appropriately named term here. x1 and x2 are possible values that the variable x could be. You're not restricted just x1, 2. This is x1, x2, ... all the way to x of n, however many states that we have. You can have random value vectors or just random values that are individual. And then in conjunction with this, a probability distribution is going to specify how likely each value is to occur. Or another way of saying that would be how likely each state is to occur. So on its own, a random variable is just a description of the states that are possible. It must be coupled with a probability distribution that specifies how likely each of these states are. And then, as well, random variables may be discrete or continuous. A discrete random variable is one that has a finite or countably infinite number of states. Note that these states are not necessarily the integers. They can also just be name states that are not considered to have any numerical value. In contrast, we can have continuous random variables, and these must be associated with a real value. So that's random variables. Let's move into probability distributions for discrete variables. When we have a probability distribution for a discrete random variable, it is referred to as a probability mass function. So before we talk about a probability mass function, we mentioned that a probability distribution is simply a description of how likely a random variable or a set of random variables is to take on each of its possible states. So a probability mass function is a probability distribution for a discrete random variable that satisfies the following criterion. The first is that the domain of P, and P here, capital P, is a representation of the probability distribution, must be the set of all possible states of X. So P must have a description or a probability of every single possible state of X. Secondly, 0 is less than or equal to the probability distribution, which is also less than or equal to 1 for all states. So in probability, 0 here is going to represent an impossible state. 0, there's a 0% probability of that state taking on that value. And then in contrast, we have a 1. This would be a 100% probability of having that particular state. So as a result, we have to maintain our probability distribution between 0 and 1. Lastly, the summation of P of x is equal to 1, and this is known as being normalized. So the summation over all possible states of P of x is going to be equal to 1. There's a 100% chance of one of the states being occupied or one of the values occurring. So we always have to sum to 1 if we have a normalized distribution, and probability mass functions are always normalized. Alright, so here's our 3 criteria for being a probability mass function. Moving on to some other types of distributions, we have joint probability distributions, and this is simply a probability mass function that acts on multiple variables. So we're not restricted to just x here. So we could have the probability distribution of x and y, and it's going to denote the probability that x and y equal 2 particular values simultaneously. So it's going to give us a probability of 2 events occurring simultaneously. Also, we have uniform distributions, and this is going to be a probability mass function or probability distribution in general, where each state of the distribution is equally likely. So for probability mass functions, this is easy to calculate since we have discrete values. Each state is going to take on the probability of 1 over k, where k is the total number of possible states. And you'll notice that uniform distributions are going to be normalized if we have k possible states, with each state having a probability of 1 over k. The summation of that is going to be k over k, which is of course 1, so there's a 100% probability of one of the states occurring. So completely normalized, equal distribution, or uniform distribution with equally likely states. So here are some 2 common types of probability mass functions. Moving on, what happens when we have a continuous variable? Well, we get a probability density function. And this is actually the type of probability distribution that you're going to see frequently throughout AI research. Probability density functions come up frequently whenever we're using continuous variables, of course. So to be a probability density function, you have to satisfy the 3 criterion, very similar to the probability mass functions. Now we write the probability density function as a lowercase p instead of a capital P, and the domain of p must be all the possible states of x as well. But notice that we have no requirement that the probability distribution is less than or equal to 1. So for continuous variables, we can have probabilities that are greater than 100%. And then instead of the summation, since we have a continuous variable here, we're going to use an integral to normalize. So the integration from negative infinity to infinity of p of x dx is going to be equal to 1. So 100% over all of the possible states. We also should talk about marginal probability. So marginal probability is going to be the probability distribution over a subset of all the variables. Oftentimes we are going to be working with marginal probability distributions in AI because we don't have all the variables, or we don't have all the data points. That is one of our sources of uncertainty that we mentioned actually in the previous lecture. So with discrete random variables, the marginal probability can be found with the sum rule. So if we know p of x and y, we can find p of x, which would just be a subset of the distribution, using the following rule. So p of x is going to be the summation of p of x over all possible y values. So for every y, we are going to take the sum of the probability of x. With continuous random variables, you might guess, instead of a summation, we're going to use the integration over all possible values of y. So we have p of x equals the integration of p of xy with respect to y, so dy here. So over all possible y values, we're going to be taking the summation, the area under the curve, to find the marginal probability. Lastly, we have conditional probability, and this comes up fairly often. It's the probability of some event given that some other event has already happened. So that can be found using the following formula. So p of y given x is going to be the probability of y and x simultaneously over simply the probability of x alone. So this is the conditional probability that y equals y given x equals x. So conditional probabilities come up frequently, and it's important to understand marginal probabilities as well as conditional probabilities, because in general we aren't going to have perfectly pristine probability distributions. We're going to be working either with a subset of the variables, or we are going to be adding criterion, which would be essentially saying what is the probability of y given x, or given a certain criterion. So conditional probabilities are used frequently as well. So that brings us to the end of our brief introduction to probability distributions. Hopefully we can put some of these into practice in a programming project in this unit. Probability distributions are going to keep coming up, so it's important to understand, or at least be able to visualize, what is going on with both probability mass functions and probability density functions. I hope you learned something new, and thank you for listening.